This video is going to look at section 10.2, where we are looking at hypothesis tests involving two means. So, let's look at this situation. The heights of 10-year-old girls can be modeled by a normal distribution, with the mean for girls being 56.4 inches, the standard deviation for girls 2.7 inches. The heights of 10-year-old boys can be modeled by a normal distribution, with the mean for boys 55.7 inches and standard deviation for boys 3.8 inches. So, suppose that we take an independent simple random sample of 12 girls and 8 boys of this age, and measure their heights. Here's what we get. Both of these sampling distributions would be approximately normal because the population distribution is approximately normal. The center would be the same as the center for the population. And remember that there is a formula for the standard deviation. You have the standard deviation divided by square root of n. Because both 12 and 8 are less than 10% of all 10-year-old girls and boys respectively in the United States, we are allowed to use that formula. But again, this is not that helpful. We need to look at the difference x bar g minus x bar b. So, we have a sampling distribution of this situation, x bar g minus x bar b. So, let's say one set of samples gave us a mean for girls of 56.09 and a mean for boys 54.68. So the resulting difference when you do x bar g minus x bar b is 1.41 inches. That's that dot there. The mean for the sampling distribution is going to be just the mean for girls minus the mean for boys, which is 0.7. And we can use our formula to calculate the standard deviation. Again, this formula is on your formula sheet. If I look at the second page of my formula sheet, under sampling distribution for means, I look at for two populations, x bar 1 minus x bar 2, I have the mean and standard deviation, just as we had on the slide. So, for the sampling distribution of x bar 1 minus x bar 2, if you have a simple random sample of size n1 from population 1 with a mean mu1 and standard deviation sigma 1, and an independent random sample of size n2 from population 2 with a mean of mu2 and a standard deviation of sigma 2, then we know that the sampling distribution of x bar 1 minus x bar 2 is normal if both population distributions are normal, and it's approximately normal if both sample sizes are large, meaning greater than or equal to 30. Or if we have a combination. So if one population is known to be normally distributed and the other sample size is large, then our sampling distribution is normal as well, or approximately normal. The mean of our sampling distribution is just mu1 minus mu2. We can use the formula for standard deviation that's listed on the formula sheet, as long as we know that the 10% condition is met for both samples. Let's look at our first example. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large cups. According to the machine's manufacturer, when a large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with mean 27 ounces and standard deviation 0.8 ounce. When the medium setting is chosen, the amount of liquid M dispensed follows a normal distribution with means 17 ounces and a standard deviation of 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled by the large setting and 25 cups filled by the medium setting. Let x bar L minus x bar M be the difference in the sample mean amount of liquid under the two settings. First, we want to know, what is the shape of the sampling distribution x bar L minus x bar M? Well, that sampling distribution will be normal because both of our populations are normal. Next, we want to find the mean of the sampling distribution, which is just the mean for large minus the mean for medium, which is 10 ounces. Lastly, we want to calculate and interpret the standard deviation. So we use the formula that's on the formula sheet. Now, there's a note here that says we do not have to check the 10% condition because we are not sampling without replacement from a finite population. There is technically an infinite population here because you have large drinks and medium drinks. We're not talking about people. So there's not really a 10% condition to check. To interpret the standard deviation, we do that the same way that we have all year. The difference, and specify which difference you're doing, so large minus medium, in the sample mean amounts of liquid typically varies by about 0.2 ounces from the true difference in means of 10 ounces. Remember, the whatever we're talking about typically varies by standard deviation from the mean. So, first we're going to look at confidence intervals. If you're constructing confidence intervals about difference in means, we have the same conditions that we have had in the past for means. First, the random condition. The data has to come from two independent random samples or from two groups in a randomized experiment. Then, 10% condition when sampling without replacement. And then the large counts condition, or the normal condition. So each sample has to either come from a population that is known to be normally distributed or have a large sample size. For each sample, if the population distribution has an unknown shape and n is less than 30, you need to make a dot plot, histogram, box and whisker plot, whichever plot you think is appropriate, to show no strong skew or outliers. So, next example. A college student wants to compare the cost of 1 and 2 bedroom apartments near campus. She collects the following data on monthly rents in dollars for a random sample of 10 apartments of each style. Let mu1 be the true mean monthly rent of all 1-bedroom apartments near campus, and mu2 be the true mean monthly rent of all 2-bedroom apartments near campus. Check if the conditions for calculated confidence interval for mu1 minus mu2 are met. So, first condition is the random condition. We are told that these are randomly selected apartments. So they are independent random samples, 10 1-bedroom and 10 2-bedroom apartments near campus. Next, 10% condition. We can assume that 10 is less than 10% of all 1-bedroom apartments near campus, and same thing with 2-bedroom apartments. That's a reasonable assumption. Lastly, we have the normal or large sample condition. The sample sizes are small. We don't know for sure that the costs of 1 and 2 bedroom apartments are normally distributed, so we need to make some dot plots. Neither shows a strong skew or outliers, so we're good. Confidence intervals are going to be set up the same way that they always are. Statistic plus or minus the critical value times the standard deviation of the statistic. In this case, our statistic is x bar 1 minus x bar 2. Now, the formula that we had used for standard deviation refers to the standard deviation of the population, which is typically not known. So, we can look at the standard error, which uses the sample standard deviation to estimate the population standard deviation. And again, this formula is on your formula sheet. In the last column, we have the standard error instead of the standard deviation. So, two-sample t-interval for difference between two means. When your conditions are met, a C% confidence interval for mu1 minus mu2 is given by this formula here. T star is the critical value with C% of the area between negative T star and T star for the T distribution with degrees of freedom using either option 1, which uses technology, which is a rather complicated formula if you were going to try to figure that out by hand, or option 2, you use the smaller number, either n1 minus 1 or n2 minus 1. The way that the calculator calculates the degrees of freedom is using this formula here. As you can see, it is not a simple formula. So, if you choose to use the calculator to find the confidence interval, that's the formula it will use. But if you are doing it by hand, just use the smaller value, either n1 minus 1 or n2 minus 1. Now, let's look at another example. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height, which they have abbreviated dBH, in centimeters. Here are summary statistics and comparative box plots of the data. Okay. So, based on the graph and the numerical summaries, write a few sentences comparing the sizes of the longleaf pine trees in the two halves of the forest. Remember that when we describe distributions, we have 4 things that we talk about: shape, outliers, center, and variability. So, shape. The distribution of dBH in the northern sample appears to be skewed right, while the distribution of dBH in the southern sample appears to be skewed left. No outliers are present. Remember, outliers would be denoted by asterisks out here. Center. It appears that trees in the southern half have much larger diameters because our median here is much higher than the median in the north. The mean and median for the southern samples are much larger than the corresponding values for the northern. You can look at the mean in the table and see the same thing. Variability. There's more variability of dBH in the northern longleaf pines. The range, IQR, and standard deviation are all larger for the northern sample. Range, you look at the length of the whiskers from minimum to maximum. IQR is the length of the box. and standard deviation is given here in our table. Next, we want to construct a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves of the Wade Tract Preserve. Again, we're going to go through the state, plan, do, conclude procedure. State, 90% confidence interval for mu1 minus mu2, where mu1 is the true mean DBH of all trees in the southern half of the forest, mu2 is the true mean DBH of all trees in the northern half of the forest. Plan, we have a 2-sample t interval for mu1 minus mu2. Checking our conditions. Random condition is met because we have independent random samples of 30 trees from both the northern and southern halves of the forest. 10% condition. It's pretty reasonable to assume that 30 is less than 10% of the trees in both the northern and southern halves. And large or normal sample. Both of our samples are 30, so we have large enough samples. Do. We need x bar 1, standard deviation 1, n1, and the same thing for the second sample. All of that is given here in this table. So we can use the 2-sample t interval function on the calculator or do the calculations by hand. If you're using the calculator, it automatically calculates this degree of freedom for you. If you're doing it by hand, you do n1 minus 1, n2 minus 1. Both of those are 29, so you use degrees of freedom is 29. And you can use the table to calculate t star, plug everything into your formula, and get your interval. I'm going to go to my calculator here. We go to Stat, Test, and we want a 2-sample t interval. If we have the data in L1 and L2, we can choose that, or we can go to Stats and type in the information that's in the chart. X bar 1 is the mean, standard deviation 1, n1, x bar 2, standard deviation 2, n2. Our confidence level, if we go back to the beginning, we want a 90% confidence interval. Now, we'll talk about this a little bit later, but you are always going to choose no for pooled. And it spits out our results. Now, I think I put that in backwards. Hold on. Yeah, we had written mu1 as the southern half, mu2 is the northern half, so I switched those. So the answers that I got were actually negative and flipped of this, but it was the same numbers. So if I had put them in the correct order, I would have gotten the same answer. For conclude, we are 90% confident that the interval here captures mu1 minus mu2, which is the difference in the true mean DBH of all the southern trees and the true mean DBH of all the northern trees. Okay, and again here, this is what I was showing you. Always click no for pooled. again, if you are using the calculator, if you have the raw data, you can do that. Type it in L1 and L2 and just select data. So if we went back to the apartments example, we could type that in L1 and L2 and spit out an interval. Exam tip. The formula leads to a lot of mistakes by students, so technology is helpful. Now, be sure that you name your procedure, which is a 2-sample t interval for mu1 minus mu2 in the plan step, and give all of the information. Give your interval and the degrees of freedom in the do step. Now, going on to significance tests. The most common null hypothesis is mu1 minus mu2 equals 0, which is the same thing as saying that the two means are equal. But you could have any value instead of 0. The conditions for a significance test are the same as they were for the confidence interval. Random, 10%, and normal or large sample. So, we look at this example. Has the mean number of hours Americans work in a week changed? One of the questions on the General Social Survey, the GSS, asked respondents how many hours they work each week. Responses from random samples of employed Americans were recorded for 1975 and 2014 and are summarized here. Did the data give convincing evidence at the alpha equals 0.05 significance level of a difference in the true mean number of work hours per week for Americans in 1975 and 2014? So, we are going to state our hypotheses and check our conditions. First, our hypotheses. Null hypothesis is that mean for 2014 minus the mean for 1975 is 0. Our alternative hypothesis is that the difference is not 0. If the problem was stated differently, because this says did the data give convincing evidence of a difference in the true mean number of hours worked? If they had said, does the data give convincing evidence that people worked more in 2014, then you would change this to be greater than 0. And again, there's a typo here. This should say mean subscript 1975 and mean subscript 2014. Are the true mean hours worked per week by Americans in those years? If we check our conditions, random. It says that we have an independent random sample of Americans from 1975 and from 2014. And 764 is definitely less than 10% of all working Americans in 1975. 1501 is definitely less than 10% of all working Americans in 2014. Because both of those sample sizes are greater than 30, we're good. So, looking at our significance test. To find our standardized test statistic, we have our generic formula here. The more specific formula for t is x bar 1 minus x bar 2 minus 0, because 0 is the value in our null hypothesis, over the standard error, which is given on the formula sheet. So, when our normal or large sample condition is met, you can find the p-value using the t distribution with degrees of freedom given by either the technology, or choose the smaller value, n1 minus 1 or n2 minus 1. Okay. It's the same thing. When the conditions are met, if your null hypothesis is that mu1 minus mu2 is 0, here's how you calculate the test statistic. Find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis, and choose your method for finding the degrees of freedom. So, finishing out this example. Explain why the sample results give some evidence for the alternative hypothesis. Well, our alternative hypothesis is that the means are different, and our means are different here. If you do mean for 2014 minus mean for 1975, you get a value that is not 0. So there is some evidence for the alternative hypothesis. Next, we want to calculate the standardized test statistic and the p-value. So we can either use the formula and then use the table, or use the TCDF in the calculator to get the p-value, or we can just use the calculator. So, if I go to Stat, Tests, to sample t-test, if I plug in all my information, so for 2014, my mean is 4191. Oops. My standard deviation is 1435, and I had 1501 people. In 1975, my mean is 38.97. Standard deviation is 1313, and I had 764 people. My alternative hypothesis was not equal to. Pooled is always no. Here, my t-value is the same that we got using the formula, 4.88. My p-value, you'll notice, is in scientific notation. So that's 0.000001158, which is the same listed here. The calculator also gave us our degrees of freedom using the crazy formula. Now, we make our conclusion. Because our p-value is way less than our alpha value, we reject the null hypothesis. There is convincing evidence of a difference in the true mean hours worked by Americans in 1975 and 2014. So, let's put it all together. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, and the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic, which is the top number, in your blood pressure for the subjects after 12 weeks, in millimeters of mercury. An increase appears as a negative number. Here's our data. So, our question is, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo on average for subjects like the ones in the study? We're going to go through our standard state, plan, do, conclude. State. Our null hypothesis is that mu sub c, the mean with the calcium, minus the mean with the placebo is 0. Our alternative hypothesis is going to be mu c minus mu p is greater than 0 because it specifically asks, is there evidence that a calcium supplement reduces blood pressure? More than the placebo. So, mu c is the true mean decrease in systolic blood pressure for healthy men like the ones in the study who take a calcium supplement. Mu p is the true mean decrease in systolic blood pressure for healthy men like the ones in the study who took the placebo. We're going to use alpha equals 0.05. Our plan section, we're doing a 2-sample t-test for mu1 minus mu2. It says that the subjects were randomly assigned to the treatments. Because we're looking at an experiment, we don't need to check the 10% condition. And the normal or large sample, we don't have large samples, so we need to check and see if they are skewed or have outliers. We also do not know that the underlying populations are normally distributed. So we make our dot plot. There's no strong skew or outliers, so we can proceed. Now, the do section. You can either do it all by hand, calculate the mean and standard deviation for each sample, then plug everything into the t-statistic formula, and then calculate the p-value, or you can do it all in the calculator. I'm going to do this in the calculator and start by typing the data into my lists. So I typed in my data. Group 1, which is the calcium group, is in L1. Group 2, which is the placebo, is in L2. Now I'm going to go to Stat, Test, 2-sample t-test, and tell it to use the data. L1, L2, keep the frequency at 1. You should never have to change that. My alternative hypothesis was greater than. Select no for pooled. Calculate. I get my t-value, my p-value, and my degrees of freedom here. If you compare what's on this slideshow that's done by hand, you get the same values. My t-value is 1.604, and then my p-value is 0.0644. And that matches what I have here for my t-value and my p-value. So, under the conclusion, because our p-value, 0.0644, is greater than our alpha value of 0.05, we fail to reject the null hypothesis. The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men who, like these, who take calcium than for men like these who take a placebo. Then we want to interpret our p-value. When you interpret the p-value, you always assume that the null hypothesis is true. So assuming that our null hypothesis, mu c minus mu p is 0, is true, then there is a, whatever your p-value is, 0.0644 probability of getting a difference, always specify the direction, calcium minus placebo, and mean blood pressure reduction for the two groups of 5.273 or greater just by the chance involved in the random assignment. Again, you can do this all in the calculator. Tip for the AP exam: the calculator is helpful, but make sure you write down all the details. You name your procedure, 2-sample t-test from mu1 minus mu2 in the plan step, and record your test statistic, which is your t, your p-value, and your degrees of freedom in the do step. One last thing, the word pooled. So, the software offers a choice of 2 different t procedures. Sometimes they're labeled unequal variances, sometimes and equal variances, but that's not the language that the calculator uses. The unequal variance procedures use our formula for the 2-sample t-interval and test. This interval and test are valid whether or not the population variances are equal. The equal variances procedure assumes that the 2 population distributions have the same variance. This procedure combines them into pools, and this is called the pooled 2-sample t statistic. Because the calculator has the option to do the first one, the unequal variance, do that. Very rarely will you know that the 2 population distributions have the same variance. So don't use the pooled procedure, because the non-pooled procedure will work regardless of whether the population variances are equal or not. So don't use the pooled option. That's it for 10.2.